Welcome to the Deep Dive. Today we're tackling, well, probably the biggest question there is. We're going beyond the questions of life and society, past things that theologians and philosophers usually handle.
We're taking these questions and subjecting them to the cold, hard lens of physics and mathematics.
And the topic today is, it's the end of everything, the absolute final end point of time itself. We're talking about cosmic eschatology.
Right. We have a pretty solid picture of the beginning. You know, the universe kicked off 13.8 billion years ago with the Big Bang. That's a story backed up by a mountain of observation.
But if there's a start to this story, there has to be an end, right? What happens in that final chapter?
And we're not talking about the Earth getting hit by an asteroid or the sun burning out. I mean, those are locally survivable in the grand cosmic scheme of things.
This is different. This is the death of the universe itself. An ending where the fundamental laws of physics dictate an inescapable final conclusion.
Yeah. There's no sequel. So our mission today is to walk you through the handful of possibilities that science currently allows for. We're going to connect the dots from the light we see from distant galaxies today to the truly extreme consequences billions or even trillions of years down the line.
And thinking about this, it really does put our own existence, right here and now, into a completely new and honestly, sometimes terrifying light.
Let's get into it.
Okay, so let's start with that term you used, eschatology. It sounds very philosophical, maybe even religious.
It is. Traditionally, that's exactly what it is. It's the part of theology or philosophy concerned with the end times. You know, you see it in Christianity, Judaism, Islam.
Right, the final judgment, a day of reckoning, that sort of thing.
Exactly. Or you see it in cyclical traditions, like in Hinduism or some Mayan beliefs, where there's this idea of recurrence, of the universe being reborn. And the key thing in almost all of those is that the end has a purpose. It's a moral restructuring or a redemptive event.
It feels like it's there to provide meaning. To say that all the suffering and chaos of the present will eventually be resolved in some just, final way.
That's the core of it. Scientific eschatology throws all of that out the window. There's no concern for meaning or justice.
It's just about the physics.
It's purely about the physics. We look at the data, the density of matter, the rate of expansion, the behavior of fundamental forces, and we follow the math to its logical conclusion. The universe's fate isn't determined by morality, it's determined by thermodynamics and gravity.
You know, for a long time, the idea of a steady-state universe was really popular. The cosmos was just eternal, unchanging. It sort of dodged this whole end times question.
It was an elegant idea, but it was completely overturned by observation.
The Big Bang.
The Big Bang, and the discovery that the universe is right now expanding. Once you know the universe is changing, that it had a definite beginning, then you have to accept it's a physical system on a timeline. And that timeline must also have an end. It's not a static backdrop. It's an evolving story.
What I find so awe-inspiring about this field is the sheer intellectual scale of it. You have scientists taking these unimaginably powerful forces, things that will literally rip space-time apart, and boiling them down to equations on a whiteboard.
It's this amazing mix of luxury and humility. I mean, here we are, this tiny species on a small rock, and yet we have the mental tools to grapple with our own ultimate cosmic doom billions of years from now. We can actually calculate and weigh the odds of these different futures based on the light we collect in our telescopes.
And to even attempt that, you have to bring together two completely different ends of physics.
You do. You have to connect particle physics, the world of the incredibly tiny, the quantum realm, with cosmology, the study of the unimaginably large.
The universe becomes its own laboratory.
It's the ultimate laboratory. We can't build a Big Bang on Earth. We can't create a black hole to study up close. So we have to look to the cosmos to test our fundamental theories. Einstein's general relativity, for instance, wasn't confirmed in a lab. It was confirmed by observing starlight bending around the sun.
And today, the biggest unanswered questions in physics are coming from the sky, not from particle colliders.
That's right. The two giant holes in our understanding are dark matter and dark energy. We only know they exist because of how they affect things on a galactic and cosmic scale. They're telling us our standard model of particle physics, our best theory of the small stuff, is missing something huge.
So understanding the very large is forcing us to rethink the very small.
Yeah.
And that's all tied up in figuring out the end of the universe.
Exactly. If we can nail down the properties of dark energy, for instance, we're not just doing cosmology. We're testing the fundamental nature of quantum fields and the vacuum itself. The beginning, the end, and the fundamental laws, they're all the same question, really.
All right, so if we want to predict the end, We have to start with the evidence we have for the beginning and the path we're on. And the key to all of this is the speed of light.
It's not infinite, and that's the trick. Because light takes time to get from there to here, looking farther out into space is literally looking back in time.
So for a cosmologist, the past isn't gone.
Yeah.
It's a place you can look at.
It's an observable region of the cosmos. We can point a telescope and watch events that happened a billion years ago unfolding right now for us.
Mm-hmm.
And if you look far enough, you can see almost all the way back to the beginning.
The Big Bang itself. Now, we should probably clear up a common misconception here.
Yes, this is important. The Big Bang was not an explosion in space. It wasn't like a bomb that went off at a single point and threw galaxies out into a pre-existing void.
That's the image everyone has, but it's wrong.
Completely. The Big Bang was an expansion of space. It happened everywhere at the same time. The entire observable universe that we see today was, in the past, squeezed into a much, much smaller, hotter, and denser state.
And the single best piece of evidence for that hot, dense state is something we can still detect today.
The cosmic microwave background, the CMB.
This is the afterglow of the Big Bang,
Yeah.
right?
It's the afterglow of creation, yeah. If you could see in microwaves, the entire sky would be glowing with this faint, uniform light. That light is the relic radiation from a time when the entire universe was a blazing hot fireball.
So you're looking so far back in time that you're seeing a point before any stars or galaxies had formed?
Before atoms, even. For the first 380,000 years, the universe was so hot it was an opaque plasma. It was a fog of free-roaming protons and electrons. Light particles, photons, couldn't travel more than a few feet without bumping into an electron and scattering.
A universal fog.
Exactly. But as the universe expanded, it cooled. And right around that 380,000-year mark, it hit a critical temperature, about 3,000 Kelvin.
Cool enough for things to settle down.
Cool enough for the protons and electrons to finally grab onto each other and form stable neutral atoms of hydrogen and helium. And in that instant, a process called recombination, the fog lifted.
The universe became transparent.
And all that light that was trapped in the fog was suddenly free to travel through space, unimpeded. And it has been traveling ever since. That light, stretched out by 13.8 billion years of cosmic expansion, is what we see today as the cosmic microwave background. That moment is called the surface of last scattering.
And there's that great story about how it was discovered by accident.
Penzias and Wilson, yeah. In the 1960s, working at Bell Labs, they had this huge horn antenna, and they kept picking up this persistent, annoying hiss.
It was coming from every direction at all times of day.
They tried everything to get rid of it. They even famously cleaned out pigeon droppings from the antenna, thinking that might be the source of the noise.
But it wasn't pigeons.
It wasn't pigeons. Meanwhile, just down the road at Princeton, a team of theorists had just calculated that if the Big Bang Theory was right, this exact kind of relic radiation should exist. They were literally building an instrument to go look for it when they heard about the guys at Bell Labs and their mysterious hiss. The two groups got together, and the rest is Nobel Prize-winning history.
And one of the key things that confirmed it was the Big Bang's afterglow is the light spectrum. It's a perfect black body curve. What does that tell us?
It's the fingerprint of a thermal object. It proves that the light came from a single, hot, uniform source that was in thermal equilibrium and then cooled down. If it were a jumble of light from, say, ancient stars, the spectrum would be all messy. Its perfection is the proof of its origin in that primordial fireball.
But it's not perfectly uniform, is it? And that's incredibly important.
Vitally important. If the CMB was perfectly smooth, the universe today would be a perfectly smooth, boring, cold gas. No stars, no galaxies, no us.
So the imperfections were the seeds.
The seeds of everything. There are these minuscule temperature fluctuations in the CMB map. Tiny little hot and cold spots on the order of just 1 part in 100,000.
And those were quantum wiggles in the very early universe.
That's the idea. Tiny quantum fluctuations got stretched to macroscopic sizes during an early period of rapid expansion. Those tiny spots were slightly denser than their surroundings, and over billions of years, gravity went to work. The rich get richer, gravitationally speaking. Those slightly denser spots pulled in more and more matter until they collapsed to form the first stars and galaxies.
So the largest structures we see in the cosmos today grew from those tiny quantum seeds visible in the afterglow of creation. That's incredible.
It's a direct link from quantum mechanics to cosmology.
Okay, that's piece of evidence number one. Piece number two is the expansion itself, which we can measure thanks to the Hubble emitter law.
Right. We know things are moving away from us because of redshift. Just like the pitch of an ambulance siren drops as it moves away from you, the wavelengths of light from a receding galaxy get stretched out, shifting it toward the red end of the spectrum.
And in 1929, Edwin Hubble noticed a pattern.
The very simple, very powerful pattern. The farther away a galaxy is, the faster it's moving away from us. It's a direct proportion. Double the distance, double the speed.
And it's crucial to understand this isn't because we're at the center of some great explosion. This is happening everywhere.
Exactly. An observer in any galaxy would see the same thing. A good analogy is to imagine dots on the surface of a balloon as you blow it up. From the perspective of any one dot, all the other dots are moving away from it. And the farther away a dot is, the faster it seems to recede.
The balloon's rubber is space-time itself stretching.
That's it. And these two pillars, the CMB telling us about the hot, dense past, and the Hubble-Lemaitre law telling us about the ongoing expansion, they give us the trajectory of the universe. They let us play the movie backwards to the beginning and forwards to its ultimate end.
All right, so that brings us to the future. With this evidence in hand, cosmologists started gaming out the possibilities. For a long time, the big question was basically, does gravity win?
It was the ultimate cosmic tug-of-war. You have the initial outward push from the Big Bang, and you have the constant inward pull of gravity from all the matter in the universe. The fate depended on which one was stronger.
It's like throwing a ball up in the air.
That's the classic analogy. If you don't throw it hard enough, gravity wins and it falls back down. If you throw it at exactly the escape velocity, it will coast away forever, slowing down but never quite stopping. And if you throw it harder than that, it'll fly away and keep going.
So the goal was to measure the critical density of the universe, the amount of stuff needed for gravity to eventually win and pull everything back.
Right. And that was complicated by the discovery of dark matter, this invisible stuff that has gravity but doesn't interact with light. But even after accounting for that, the answer was ambiguous until the late 1990s.
So let's talk about the first major scenario, the one where gravity wins, the big crunch.
This was the leading contender for a while. The idea is that if the universe is dense enough, the expansion will eventually slow down, stop, and then reverse.
What would that look like from our perspective, billions of years from now?
Well, the first sign of doom would be that we'd see the expansion stopping. Distant galaxies would no longer be redshifted, and then they would start to be blue-shifted.
They're coming towards us.
And coming faster and faster. The whole universe would be falling back in on itself. As it got smaller and denser, the ambient temperature of space itself would start to rise.
So it's a fiery end.
A very fiery end. The background radiation would get so hot it would cook planets and vaporize stars long before anything actually collided. The universe would get hotter and hotter, denser and denser, until everything collapsed back into an infinitely hot, dense singularity. A reversal of the Big Bang.
An absolute, total obliteration.
And for some, a hint of rebirth. Some cyclic models imagined that crunch could trigger a new Big Bang. But for our universe, it would be the definitive end.
But then the data came in, and it turned out the universe wasn't slowing down at all.
It was the shock of the century in cosmology. In 1998, two separate teams were trying to measure precisely how much the expansion was slowing down. They were using a special kind of exploding star as a yardstick.
Type Ia supernovae. We need to pause here because these are so important. Why are they called standard candles?
They are the gold standard for measuring cosmic distances. A type Ia supernova happens when a white dwarf star in a binary system pulls too much material off its companion star.
It gets too greedy.
It gets too greedy, and when its mass hits a very specific critical limit, the Chandrasekhar limit, about 1.4 times the mass of our sun, it triggers a runaway thermonuclear explosion.
And because they all explode at the exact same mass.
They all have the exact same intrinsic brightness. They're like cosmic 100-watt light bulbs. If you see one that looks dim, you know it's far away. If it looks bright, you know it's close. By measuring how dim they appear, you can calculate their distance with incredible precision.
So the teams measured these distant supernovae, expecting to find them a little brighter than they should be, because the expansion should have been slowing down.
That was the expectation. What they found was the exact opposite. The distant supernovae were dimmer than expected.
Meaning they were farther away than our models predicted.
Farther away. Which could only mean one thing. In the time it took their light to reach us, the expansion of the universe hadn't been slowing down. It had been speeding up, accelerating.
And they completely changed the game. Suddenly, gravity wasn't winning. Something else was pushing back.
Something else was pushing back, and it was winning. This discovery forced cosmologists to resurrect an idea Einstein himself had called his biggest blunder, the cosmological constant. We now call this mysterious force dark energy.
So this dark energy is a kind of anti-gravity, woven into the fabric of space itself.
That's the leading theory. It's a property of the vacuum, an energy inherent to empty space that has a negative pressure, which creates an outward push, and it's dominant. Right now, about 68% of the energy density of the universe is dark energy.
So with that discovery, the big crunch was essentially off the table, and the future suddenly looked very different.
It did. The question then became, what is this dark energy? Is it constant? Does it change over time? And the answer to that question determines our ultimate fate.
Okay, so let's go to the most likely scenario, based on our current data. This happens if dark energy is a true cosmological constant, an unchanging property of space.
If the equation of state parameter, which we call W, is exactly master 1, this leads to scenario B, the heat death.
Also known as the big freeze.
Yeah.
And it's a slow, drawn-out agony.
It's a tragedy of ever-increasing isolation. The accelerated expansion just keeps going forever. As space stretches, it drags distant galaxies away from us faster and faster.
Eventually, it drags them away from us faster than the speed of light.
Exactly. They cross something called our cosmic event horizon, or the Hubble radius. Once a galaxy crosses that boundary, the space between us and it is expanding so fast that its light can never reach us again, no matter how long we wait.
So we're watching the universe disappear.
Literally. One by one, the distant galaxies will wink out of our sky. Eventually, even the galaxies in our local supercluster will be carried away until all that's left in our sky is our own Milky Way galaxy, which will have merged with Andromeda and our other local neighbors. We'll be a single, massive island galaxy in an endless, empty, dark void.
And once that isolation is complete, the universe begins to truly die.
Yes. The decay starts. First, over trillions of years, all the gas and dust will be used up and star formation will cease. The last stars will burn out and die, leaving only stellar remnants, white dwarfs, neutron stars, black holes.
But even matter itself isn't forever.
Probably not. Our best theories suggest that protons themselves are unstable over immense timescales. They might decay in something like 10 to the power of 33 years.
So atoms themselves dissolve into radiation.
But that's the idea. The universe becomes a thin soup of photons and leptons, and the only organized structures left are the most durable things in the cosmos. Black holes.
But even they don't last forever. They evaporate through Hawking radiation.
Let's unpack that because it's such a wild concept. It's pure quantum mechanics. Empty space isn't really empty. It's fizzing with virtual particles that pop into and out of existence in pairs.
A particle and an antiparticle.
Right. They appear, exist for a fleeting moment, and then annihilate each other. But if a pair happens to pop into existence right on the edge of a black hole's event horizon,
one can fall in and the other can escape.
and the one that escapes becomes a real particle, carrying energy away from the black hole. To an outside observer, it looks like the black hole is glowing very, very faintly. It's losing mass, it's evaporating.
And this takes an unbelievable amount of time.
For a supermassive black hole, we're talking about 10 to the power of 100 years.
You'll go.
A Google. Far, far longer than any other timescale we've discussed. But eventually, even the last black hole will fizzle away into nothing but a final poof of radiation.
And after that, what's left?
Nothing. A universe that is cold, dark, and almost perfectly uniform.
Ugh.
A vast, dilute, ever-expanding sea of low-energy photons and particles.
But the real killer here, the reason nothing can ever happen again, isn't the cold. It's entropy.
It's the second law of thermodynamics, taken to its ultimate conclusion. Entropy, which is a measure of disorder, must always increase in a closed system. And the heat death is the state of maximum possible entropy.
Everything is perfectly spread out, no temperature differences, no density gradients, nothing.
And if you don't have gradients, you can't have complexity, you can't do work. Life, thought, computation, all of these processes require energy flowing from a hot place to a cold place. In a universe at thermal equilibrium, no processes can occur. Time itself becomes meaningless because if entropy can't go up, nothing can change, nothing can happen.
And that leads to a really disturbing philosophical problem with an eternal universe like this, the Boltzmann brains.
This is one of the weirdest and most troubling ideas in physics. If the universe lasts for an infinite amount of time in this quiet, high-entropy state, quantum mechanics says that random fluctuations will still happen.
So just by pure chance, things could pop back into existence.
Given infinite time, anything that is not impossible is inevitable. So yes, a new low-entropy state, like a new Big Bang, could theoretically fluctuate into existence.
Okay, that's hopeful. A cosmic reset button.
But here's the problem. A brand new universe is an incredibly complex low-entropy configuration. The statistical likelihood of that happening is astronomically small. What's far, far, far more likely to fluctuate into existence?
Something simpler.
Much simpler. For instance, a single conscious brain, complete with a full set of false memories of a life lived in a complex universe. A Boltzmann brain.
Wait, so you're saying it's more probable that a random thinking brain would just pop out of the void than an entire universe?
Vastly more probable. And if that's true, and if we live in a universe that will last forever, then statistically, you and I are almost certainly not real people in a real universe. We are Boltzmann brains having a fleeting moment of consciousness with implanted memories.
That's unsettling. It completely undermines our ability to trust our own observations.
It's a huge problem. It leads many physicists to believe that the universe can't be eternal, that some other process must intervene to destroy it before these fluctuations can dominate, ensuring that our observations are, in fact, reliable. Which brings us to the more violent possibilities.
Right, so heat death is what happens if dark energy is constant. But what if it's not? What if it gets stronger over time?
This is scenario C, the Big Rip. This happens if the dark energy is something we call phantom energy, where its density actually increases as space expands.
So it's a runaway feedback loop. Expansion creates more space, which creates more phantom energy, which drives even faster expansion.
It's a terrifying positive feedback loop. And unlike the heat death, which takes practically forever, the Big Rip happens in a finite, calculable amount of time.
And it is the most complete form of destruction imaginable.
It's destruction on every single scale, in sequence.
Hmm.
First, billions of years from now, the phantom energy's repulsive force will become stronger than the gravity holding clusters of galaxies together. They'll fly apart.
And it comes for the galaxies themselves.
Yes. A few million years before the end, it will overcome the gravity holding individual galaxies together. Stars will be flung into the void. Then, just months before the end, it will be stronger than the gravity holding planets in orbit around their stars. The Earth will be torn away from the sun.
And then it gets even worse.
Much worse. In the final minutes, planets and stars themselves will be torn apart. Then, in the final fractions of a second, the phantom energy becomes stronger than the electromagnetic force.
The force that holds atoms together.
Atoms will be ripped apart. Your body would be disintegrated into a cloud of unattached electrons and nuclei. And in the very last moment, the force becomes infinitely strong, overcoming even the strong nuclear force that holds atomic nuclei together.
And then?
Even space-time itself is torn asunder. The universe ends not as a cold void, but as an infinitely expanding singularity of disconnected fundamental particles, the ultimate annihilation.
And the frightening thing is the difference between the parameter that causes a slow heat death and the one that causes a big rip is tiny. It's a measurement we're still trying to pin down.
That's right. The line between W equals 1 for heat death and W being slightly less than number 1 for a big rip is within our current margins of error. This is one of the biggest reasons we have things like the Hubble tension debate. Precisely measuring that expansion rate today could be the clue that tells us whether we're doomed to a freeze or a rip.
Okay, so we have the slow freeze and the violent rip. But there's one more scenario, the wild card. The one that could happen at any second with no warning at all.
This is the scariest one, in my opinion. Vacuum decay.
This has nothing to do with gravity or expansion. This is about the fundamental stability of reality itself.
It's pure quantum field theory. It comes down to the Higgs field, the energy field that permeates all of space and gives fundamental particles their mass. The laws of physics as we know them are based on the value or the energy state of that field.
And the problem is our universe might be in the wrong state.
Our best measurements of the Higgs boson's mass suggest that the Higgs field might be in what we call a false vacuum. Think of it like a ball resting in a small dip on the side of a much deeper valley. It's stable for now, but it's not in the lowest possible energy state.
There's a true vacuum out there, a state with a lower energy level.
And if the Higgs field ever, for any reason, transitions to that true vacuum state, the universe is over.
What happens in that new state?
The laws of physics change. The fundamental constants that govern chemistry and nuclear physics would take on new values. The interactions that allow atoms to be stable, that allow electrons to orbit nuclei, would cease to exist. All organized matter would become instantly unstable.
And how would this transition spread?
It would start in one tiny point, anywhere in the universe. A little bubble of true vacuum would form, and because it's at a lower energy state, this bubble would expand outwards in all directions, converting the false vacuum into true vacuum as it goes.
The bubble of death.
The bubble of death.
Yeah.
And the truly terrifying part is its speed. It would expand at the speed of light.
Which means you could never see it coming.
Never. The light from the approaching bubble wall is traveling at the same speed as the wall itself. There would be no warning. One moment, you're here. The next, the bubble wall hits you. And you, the Earth, the Sun, the galaxy, everything is instantly converted into a burst of energy and exotic particles governed by new hostile laws of physics.
So, what could trigger it?
Two things. One is a brute force approach. A particle collision with an absurd amount of energy, something far beyond what even cosmic rays produce, could knock the field over the barrier into the true vacuum.
But the other way is much weirder.
The other way is pure quantum weirdness. Quantum tunneling. Just like a quantum particle can sometimes pass through a solid wall, the Higgs field itself, just by chance, could spontaneously tunnel through the energy barrier and into the true vacuum state.
So it could happen at any time, for no reason at all.
At any moment, anywhere in the cosmos. Now, the calculated probability is fantastically low. The current estimates suggest our vacuum is probably stable for at least 10 to the power of 100 years, far longer than the age of the universe. So you probably don't need to lose sleep over it.
Probably.
But the chance is not zero. It is the ultimate, instantaneous, universe-ending wildcard.
Wow. Okay, so trying to figure out which of these fates is ours, it feels like it requires a complete unification of physics.
It does. You need to understand both general relativity, the theory of the very large, and quantum mechanics, the theory of the very small. And as we've said, the biggest clues right now, dark matter and dark energy, are coming from cosmology, pushing particle physics into new territory.
So let's talk about the tools that are trying to solve this. What are the next generation instruments that will help us narrow down the possibilities?
The big one coming online is the Vera C. Rubin Observatory, or VRO. Its main project is the Legacy Survey of Space and Time, the LSST.
And its goal is basically to make the ultimate map of the universe.
That's a good way to put it. Over 10 years, it's going to map something like 10 billion galaxies and millions of new supernovae. This will give us an unprecedentedly detailed history of the universe's expansion. We won't just know how fast it's expanding now, we'll know precisely how that acceleration has changed over billions of years.
And that will help us nail down that W parameter to see if we're headed for a freeze or a rip.
Exactly. And we can combine that map with our maps of the cosmic microwave background to do something called CMB lensing.
What's that?
As the ancient light from the CMB travels to us, its path is slightly bent by the gravity of all the stuff it passes through. Galaxies, dark matter, clusters, it gets distorted.
So you compare the map of where the stuff is with the map of how the light is bent.
Right, and that lets you test if gravity is behaving the way Einstein said it should over cosmic distances. If what we call dark energy is actually a sign that gravity itself works differently on large scales, this is how we'll find out. It helps us rule out alternative theories.
We also have new tools like LIGO, the gravitational wave detectors. How do they fit into predicting the end of the universe?
They give us a completely new and independent way to measure distances. When two neutron stars collide, they send out both gravitational waves and a flash of light.
And the gravitational wave signal tells you exactly how far away it was.
With incredible precision. And the light tells you its redshift or how fast it's receding. Put them together, and you get a brand new measurement of the Hubble constant, the expansion rate. This could be the tool that finally resolves the Hubble tension and gives us a much better handle on the nature of dark energy.
So all this data might push us beyond our current standard model. And theorists are already working on some pretty radical ideas for what might lie beyond.
Oh, yeah. I mean, one of the biggest mysteries is still just how weirdly weak gravity is compared to the other forces.
Right. A simple fridge magnet can beat the gravitational pull of the entire Earth.
And one wild idea to explain that is the concept of extra dimensions, the brain world hypothesis.
This is the idea that our 3D universe is like a membrane, a brain, floating in a higher dimensional space called the bulk.
Exactly. And in this model, the other forces are stuck to our brain, but gravity can leak out into the bulk. And because it's spread out over these extra dimensions, it appears much weaker to us here on the brain. Highly speculative, but it's a fascinating idea.
It also opens the door to other cosmic models, like cyclic universes, that try to solve the problem of why our universe started in such a perfectly ordered, low-entropy state.
That's a huge question. It's statistically very unlikely. So models like the ekpyrotic universe propose that our Big Bang wasn't a beginning, but a bounce from a previous contracting phase. Or maybe a collision between two brains.
And then there's Roger Penrose's conformal cyclic cosmology.
A beautiful, mind-bending idea. He suggests that the end state of one universe, a cold, empty heat death, actually becomes mathematically identical to the Big Bang of the next. The universe forgets how big it is, in a sense, and that allows a new cycle to begin. He even thinks we might be able to see faint traces of the previous universe's black holes in our CMB.
So whether it's bounces or rips or decay, our understanding of our ultimate fate is constantly evolving with the data we're gathering right now.
Absolutely. We're in a golden age of cosmology.
Okay, so after all of this, after contemplating the big rip and vacuum decay and the endless cold of the heat death, we have to come back to the human scale. What does all this mean for us?
It's a heavy question, and for many people, the first reaction is, well, dread, a sense of meaninglessness.
If everything's just going to decay into nothingness, if all our art and science and history will eventually be erased without a trace, then what's the point?
It's a natural reaction. It can feel like it strips away the comfort of permanence. Our sources mention that this realization often makes people pivot from these cosmic timescales back to our immediate ones.
Right. Suddenly worrying about the heat death trillions of years from now seems less important than worrying about climate change in the next 100.
The cosmic perspective can be humbling in that way. It clarifies our immediate priorities. But there's another reaction, too, a sense of profound awe.
The idea that we are lucky enough to exist in this brief, interesting window of cosmic history when stuff is actually happening, when the universe is full of stars and life and complexity.
We live in the very interesting blip. And not only that, we are a part of the universe that has become conscious of itself. We are temporary beings capable of understanding the eternal laws that govern our own beginning and end.
There's a kind of transcendence in that, isn't there? In the act of understanding itself.
I think so. You get to touch something timeless in the concepts themselves, even if our physical existence is fleeting. The knowledge itself becomes the legacy.
You know, the physicist Freeman Dyson spent years trying to figure out how intelligent life could survive forever in a cooling universe. But his plans were all based on a universe that was just slowly coasting.
And the discovery of accelerated expansion of dark energy made all his plans impossible. The universe is running away from us too fast, nature gets the final vote, and we have to accept that.
And yet, as another cosmologist, René Lejeune, put it, there's something freeing in that knowledge.
She called the heat death cold and beautiful. And I think what she meant is that realizing our efforts can't change the ultimate fate of the universe is, in a way, liberating. It frees us from that cosmic pressure.
So our purpose isn't to save the universe, it's to understand it, to appreciate it.
To enjoy the journey while we're on it, and to marvel at the fact that a fragile, temporary consciousness like ours can map the boundaries of existence and even quantify its own destruction. That, paradoxically, might be our greatest triumph.
The universe might be finite, but our ability to comprehend it seems to be accelerating.
Thanks for joining us. If you'd like to watch the mini explainer for this topic, click the link in the description and explore the full Critical Thinking Deep Dives playlist for more long-form episodes.